tonight's guest lecturer is one of our very own from the mathematics department, Dr. Justin Lambright. He got his BA in applied math and physics from Geneva College. He got his master's degree from Western Illinois and his PhD from Lehigh in mathematics. So he's been at AU, this is his 4th year, and tonight he's going to explain to us the beauty of mathematics. And we're glad you're here. He tells me I don't need to know too much math to follow along, so hopefully I'll be able to follow. So Dr. Lambright.
All right, well, thank you very much for coming, and thank you for the opportunity to come. I will try to say a little about the beauty of math, but that's sort of a hard thing to do in an hour, explain all of it. I just muted things, not turned the lights off. There we go. All right, so the title says Exploration of Math, Simply Beautiful and Astounding. And I just totally turned the lights off on myself, but I'm wearing a shirt today that the math department chose and made 2 years ago. We put it out to the seniors in college, so we gave them a vote of what they wanted on the shirt. And they ended up choosing this equation. The equation you see up here, e to the I pi plus 1 equals 0. It's known as Euler's identity. And I have a quote up here from Keith Devlin. Does anyone know who Keith Devlin is? He's about as famous of a math person as you can get. He's NPR's math guy. So he's a guy on NPR that they talk to whenever they do math. So, like, again, that's about as famous as you can get as a math person. He said, like, Shakespearean sonnet captures the very essence of love, or painting that brings out the beauty of the human form that is far more than just skin deep. Euler's equation reaches down into the very depths of existence. If you Google beautiful math or mathematical beauty, this equation pops up quite a lot. Okay? Now, a lot of people find beauty and math as sort of two separate things that don't overlap, and so this might seem a little strange to you. And why is he talking about Shakespeare and paintings and stuff like that in the depths of existence about some crazy little math thing? So what I would like to do today is walk through the pieces of the puzzle that are up on the screen, and hopefully we can understand a little bit about what each one means and how they come together into this wonderful little equation that is quite surprising and actually tells us quite a bit about our created world. So, we'll start with the pieces. First part, equals. The equality relation is pretty much the main thing in math, right? Think about everything you do in math. Equals, right? The calculator, bunch, equals. Pretty much the big idea we're interested in is showing that two quantities are the same. So I think we got that down. I don't have to talk too much about equality. There are 3 operations represented. Plus, addition right here, which we all know, right? 4 plus 3, what does it mean to add 2 things? Basically, test a set of 4, a set of 3, put them together into one big set, and we've got 7, right? My 3-year-old daughter does not know what this means yet, but hopefully she will soon, by the time she's like 5 or 6, right? This is something we learn very early. The next operation we'll learn about is multiplication. Multiplication, do we see that on the previous slide? Well, actually, yeah, right here, I times 5. We dropped the symbol, right? But that really means multiplication. So we do have multiplication, even though it's hiding, sort of sneaky. What is multiplication? It's just repeated addition, right? It's just a shortcut for doing addition. So addition is where we start. We invent this thing called multiplication, which is really just a shortcut for addition, so everything's really just addition. And then exponentiation, we saw something with an exponent, 4 to the 3rd. That just means repeated multiplication, but repeated multiplication is really just repeated addition, so exponentiation, big word, can't say it, is really addition. So if you think about it, all we ever do in math is add. Doesn't make it sound so much easier, but of course it gets a little bit more complicated, but in a sense, that's what we're doing. Now those were the operations and the relations, but there are 5 other symbols representing numbers. So, first number we see 0, which, does anyone know what this guy's from? Schoolhouse Rocks, right? 0, my hero, good song. 0 is pretty awesome. It's a great number. It doesn't just represent nothing, it is not important. It's actually a very important part of our mathematical system. Without 0 as a placeholder, our whole base 10 system falls apart. It's the additive identity, it's got all kinds of nice properties. 0 is fundamentally one of the more important parts of math, right? Next number, 1. We got a little orange, let's go Ravens. 1 is sort of the basic number, right? What's 2? 1 plus 1. What's 3? 1 plus 1 plus 1. What's 4? 1 plus 1 plus 1. So in a sense, all we ever do is add and use the number 1. Right? We build up all the numbers with this. It's quite simple. Math is just adding and the number 1. I think I got this. Right? Somehow out of that we end up with calculus and higher math. But But it's quite simple. So in a sense, 1 is very fundamental, 0 is very fundamental. Then we get the weird looking Greek letter and our regular old good American letters. They're not really American, right? Phoenician or something like that. But what were sort of standard, E, I, and pi. So what are these numbers? Pi, 3.14, 159, 26, and it goes, and it goes, and it goes, and it goes, right? We're familiar with this, sort of our classic irrational number. We see it in geometry. We feel we got some understanding. We'll talk a little bit more about what pi is. E, are we familiar with that? Anyone who's in calculus is familiar with that, or you haven't been paying attention. And that's a bad sign, because we're probably going to take calculus again in January. But E comes up in calculus. It's very, very important to see where that comes from. And then this guy, we seem to forget about a lot. We don't actually teach much with that here in our whole curriculum, which is sad, because I is really awesome, and I like talking about myself. I'm self-centered, so I like that. Anyway, I is the square root of negative 1, and we'll talk a little bit about why in the world we talk about this imaginary thing. Right? Math is concrete. We solve problems. Yes. We like math. 2 plus 2 is 4. I can do it. Why in the world would we do something imaginary? That doesn't really jive with our idea of math, but we'll talk about that as we go. So let's start with pi. Pi, the letter, is just, they picked it, right? There's nothing special about pi other than what they decided. This is going to represent the ratio of the circumference to the diameter of a circle. Neat thing about circles, no matter how big I make this, the circumference, which is all the way around, and the diameter, which is across the middle, that ratio is always the same, no matter how big or small my circle is. That's actually sort of neat, the sort of similarity idea in math. Geometry is a big deal, and we give this special number a letter, pi. All right? Now, interesting fact. It's a ratio, right? I defined it as a fraction. Surprise, surprise, this is not rational. There's no way to represent this and write equals some integer, a sort of normal whole number, and another whole number as a fraction. So somehow it's irrational, not expressible in a fraction form, even though we defined it that way. It's sort of mysterious. And in fact, the Greeks and the people who first started this had some serious issues with that. Okay, they wanted it to be irrational. They didn't like the idea of an irrational number. They spent a lot of time trying to figure out what rational number is it, which you can't do because it's not, but they had to figure out it's not. And so one way we can do this is to approximate a circle by a polygon, right? I can put a pentagon inside and a pentagon outside. I can take a hexagon inside and a hexagon outside. I can take an octagon and an octagon. I can go up to n-gons. This is a good thing in math. We stop coming with prefixes, we just say n-gon. So that like, you don't have to. It's sort of a nice little trick. But notice if I make more and more sides to my polygon, what's happening? The outer and the inner one are getting closer together. And so we can sort of imagine a circle as what happens if I allow for an infinite number of sides. So we can sort of think of it as an infinite number of sides, and by understanding what the ratio of the perimeter of a polygon compared to its diameter is, we can get an estimation or some idea of what pi really is. Okay? And for those of you who are in calculus or have had calculus, this process of repeating it over and over to get closer and closer and closer and closer and closer and closer. Too bad there was a cat there and chased the light. A closer and closer approximation of a number, we call that the notion of a limit. And that's sort of the fundamental idea behind calculus. And we'll see that again as we continue. So, pi shows up in our magic formula, but where else does pi show up? It's actually very important. It shows up in a lot of ways. Circles, spheres, not surprisingly, they're round. All right? But interestingly enough, in physics, Heisenberg's uncertainty principle, a big part of our quantum mechanics and understanding there. What do we see? We see 4 pi showing up. Coulomb's law. What does Coulomb's law have to do with it? We've learned about this. Somebody in this room has had to learn about Coulomb's law.
Electricity. Electrical charge.
Electrical charge, right? So we've got electrical charge. Something to do with electricity, which clearly has to do with circles. Right? Circuits. I don't know. There's a 4 pi thing, right? And then the cosmological, where's John Mills? Cosmological constant, I can't say that, which is this funny little capital lambda thing. And once again, we see a pi. So I'm trying to understand sort of the fundamental nature of our universe, pi pops up again. And there are tons of examples of these. I could have made slide after slide of formulas in physics, chemistry, probably even biology somewhere. I haven't studied that much biology, sorry. But pi shows up a lot. So strangely enough, this idea of a circle is somehow connected to bigger features. So Before we leave circles, I want to talk about something we're going to come back to later. Okay, so this is sort of a preview of something to come. Angles. So we're familiar, most of us, with the idea of degrees, right? How many degrees are in a circle? 360, right? But the radian is actually a somewhat better one because it gives us math problems to assign for students. And it actually is a standard angular measure. So what the radian is doing with these really bad pictures is, if you think about a radian, imagine a unit circle. So the radius is 1. Well, it doesn't really matter what the radius is, but the idea is if you take the length of the radius and you trace out that distance along the edge, this distance here is equal to the distance there. Can we see that? So we go that same radius distance around. Then the angle created by that is what we call 1 radian. So if you think about it, radius, radian, sort of connect. So that's actually what 1 radian is. I'm traveling 1 radius along the outside. So this is actually a nice fundamental unit in some sense. And so if you think about it, you measure out, you get 1, 2, 3, 4, 5, 6, and a wee little bit. And it turns out, if we do some algebra with the whole pi equals circumference over the diameter, right? This 6 and a wee little bit makes up the circumference. Pi and the diameter, move the diameter to the other side, you get circumference equals 2 pi r, because diameter is 2r. And what we end up noticing is that this is 2 pi times the radius. Well, that would mean it's 2 pi all the way around radius. Okay? So doing a little algebra, I don't know who else do that for me, but we do some algebra, and we end up with that the whole way around the circle is 2 pi, and so halfway would be pi radians at 180 degrees. Okay, and so this factor is going to be important later. That halfway around the circle is what we call pi radians. So when you see pi show up, you can think about circles and circumference of and diameter, but you can also think of 180 degrees. So think of it as circle 180. Okay? Next number. Of course, it's actually a letter E, but it represents a number, so we'll call it a number. Euler's number. So we name it after Euler, we got E. So this is totally not Euler. Right? We named it after Euler, but he's not the guy who figured it out. This is something weird in math. Usually we name things after the guy who figures it out, or the lady. But in this case, we name it after somebody totally different because he's more famous. I'm not sure why it's Euler. But Bernoulli, Jacob Bernoulli, there were a couple of Bernoullis that did some good math. He was around in the late 17th century, I believe, right around the time when Newton was coming up with calculus and was sort of developing. Bernoulli was a contemporary. He was reading this stuff and like, whoa, awesome, cool math. Okay, but what he was interested in is what any good, warm-blooded American is, making money, right? That's the whole American dream. Come in, work hard, make money, make yourself better than you were before. So we're focused on some money, so he thought, let's get rich, let's learn math so I can get rich. Strange enough. It might work right, sorry. Anyway, maybe. So what he was studying was compound interest. And compound interest, notice in this picture, you've got this little slope line. Simple interest is where each, 5% interest. So at the end of the year, you earn 5% on your first year. End of the next year, you earn that same amount of interest. The idea of compound interest is that instead what we do is we take the interest you earn 1 year, put it in, and that becomes part of our principal, so we earn interest on the interest. And then the next month we earn interest on that interest, and we earn interest on that interest. And because it builds, we get this nice speeding up effect. Notice it's getting steeper and steeper, and we speed up and we make a lot more money. Okay? So we've got this idea of compound interest. Or if we're the lender, we get to charge more interest and we make more money, so either way, we're happy, right? So he was studying compound interest, and he noticed that if you compound more frequently, so you could say, okay, I'm going to calculate my interest at the end of the year. Or you could say, let's calculate at the end of each month, or at the end of each day, or at the end of each hour, okay? So he decided to calculate the interest period time, that did not sound right, conversion periods, that's the word I want. More frequently, you make more money. So in this example, I have come up with $1,000 principal. So start with $1,000. Interest rate of 5% for 5 years. What's going to happen? How much money will I have after 5 years if I just put $1,000 in this 5% and let's say. And so M is representing the number of times I compound per year. So if I just did it once a year, M is 1. And what you find out is you end up with $1,276.28. So you made a whopping $276. It's not too bad in 5 years. But if you speed it up to quarterly, so every 3 months, you get a little bit more, right? About $4. If you go up to monthly, you made another $1.30. If you go up to weekly, it only increased by 50 cents. Go up to daily, we only went up, what, 13 cents? 1,000 times a year, 2 cents, and by the time I'm up to 100 million, I've only gained 1 cent. So notice what's happening is small changes here resulted in bigger changes, and as I go, I can change this by 100 times and barely make a cent. And so the idea was, let's try and make as much money as possible, right? So let's do this as frequently as we can. But oddly, there's sort of a limit. There's sort of like a boundary. I can crank this up to 1 with 100 million zeros after it, and I'm only going to get another half a cent or so. So it's like you're speeding up, but you're not. It's sort of slowing down. And so we end up with the idea of a limit. So what he did is he sort of said, what happens if n goes to infinity? And at this time, he was reading about calculus and this idea of infinitesimals and limits and all these wonderful ideas. And so he asked himself, what happens if I take 1 plus 1 over n to the n? Notice all I'm doing is letting r be 1, the principal be 1, the t be 1. Basically wipe out everything except the important piece. What's the important piece here? M. That's what's changing stuff. So let's eliminate all the distractions, focus on just that, and ask myself, what happens as I make n bigger? So here I have a graph. So I'm letting n be 2, 4, 6, 8, 10, 12, and see how it gets bigger and bigger, but it starts to flatten off, right? And what you realize is there's this boundary, this blue line that never gets passed. It just gets closer and closer. And he called that E. And that ends up being the first place we ever studied in our development. Okay? In calculus, we don't teach you this. Instead, we define E in terms of the value of the base of an exponential where the first derivative is equal to 1 at some point, and we get really crazy. But historically, this is where it first popped up. And so this weird 2.7182818 go on forever number is sort of the limit of compound interest. And again, we're just trying to make money. And yet this somehow becomes fundamental to the universe in a lot of ways, which is sort of bizarre, right? So money really does make the world go around. Maybe not, but it seems like. One more comment here. What's special about pi? It goes on forever, never repeats, no pattern, totally cool and unique, right? E does the same thing. And in fact, there are more numbers that do that than numbers that don't. Sort of strange, right? Want to know more about it? Take a math class. Anyway. But actually, it's really not that strange that have numbers that go on forever and never repeat. There are actually more, infinitely many more. Infinity, it's fun stuff. Size of infinity, that's a good another question. But notice in this idea, we were taking a limit. We were saying, what happens if m blows up and goes to infinity? My sequence is sort of stopping. It's reaching some boundary or limitation. And so in calculus, the fancy way we do this is we say we have a sequence of numbers, and L is the limit if I can make xn arbitrarily close to L, as close as I want, just by letting n get big enough. So say I want to be within 0.0000005. Well, if n is 500 million, it will be. And if I can always do that, we say that that's the limit. It's saying I can get as close as I want just by going far enough. And so, for example, if I have a sequence of 1 over n, so 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and I just make the fraction smaller, it gets smaller, smaller, and smaller, and it approaches 0. And so notice I have a little picture that some of you from calculus might remember about epsilon band. But basically what I'm saying is if I want it to be within a quarter, I just come out here to 4, and now from here on out, this red line is trapped between those two blue. It's as close as I want. If I wanted to be within a tenth, make n 10, and I'll be within a tenth. If I wanted to be within a millionth, make n a million, and from then on I'm trapped. Okay, so this idea of what's happening as I approach. Now, this is the fundamental idea of calculus. It's really all about limits. But calculus focuses on two geometric questions, slope and area. So I'm going to take a little diversion. I guess a better word would be a tangent. So we'll take a little tangent into calculus. And why is it a joke for those who don't understand why we're laughing? Because one of the first things we learn about calculus is the idea of slope. And the question is, if I have a graph and I have a line which is tangent to it, so it just sort of touches right there at that point, sort of kisses the graph, keeps on going in the same direction, I want to know what that line is, so I need the slope of the tangent. And that's sort of the first part of calculus, is finding derivatives. In order to do that, what we can do is sort of approximate. Take a point on the curve and draw the line between them. Is this line anywhere near the blue one? No. But as I get closer, is that one better? A little bit. As I get closer, better. So as I move this point here closer and closer to the point I'm interested in, my secant lines get closer to my tangent. And so we can define and figure out what the slope here is by figuring out the slope of each one of these and saying, let's take the limit as I get closer to A. And so all we have to do is understand how to take limits, and we can figure out this problem. Similarly, the other area we're interested in is area. That was a bad sentence, area twice at the same time. Sorry. But the other question we're interested in is area. So say I wanted to know the area under this curve. Well, I can approximate it by making rectangles. That's a really bad approximation. Or I can make more rectangles, or more rectangles, or more rectangles. And notice as I tuck skinnier and skinnier rectangles in, they fill up the space underneath the curve a lot better. And so again, what I can do is say, if I want to know the real area, all I have to do is make the number of rectangles I have go off to infinity. Take the limit. And so to answer these two questions, all you have to do is understand limits, and that's what calculus is all about in a nutshell. The nice thing is, tangent line has to do with rates of change. Anytime you have something changing, you can represent it with calculus as a derivative. And then areas also have a lot of nice things like displacement in physics and other applications. And so both of these can be extended to all kinds of really nice physical problems, and even things like money. We always like to go back. So now that we took our diversion or tangent to calculus, let's go back. Where are we actually going? The point of today's talk is identity, right? It's supposedly very beautiful. On my chest, maybe not so. But this is, beauty right here, and there's one piece we haven't talked about, which is I. So I have a nice little quote from Albert Einstein. You can't really read it here, but this is actually something Albert Einstein said. Imagination is everything. It's a preview of life's coming attractions. A physicist talking about imagination. I don't think that's that strange, considering the stuff they come up with. You have to have quite the imagination to come up with that, right? Well, what can we do as mathematicians? We can use our imagination, right? And we can imagine a number called I, which when I squared is -1. Why is this using my imagination? We take any real number, right? Positive times positive is positive. Negative times negative is positive, right? There's two wrongs make a right. Two negatives make a positive, right? So we get a positive. So if I take any number times itself, that's what squaring is, I get a positive. So no number squared is positive. So we have to imagine, well, let's pretend there is a number which when I square it ends up being -1. So this is not a normal number. It's not something we're used to. It's something new. So I'm using my imagination. Totally creative, right? It's not, finger paint or anything like that. But it is imaginative. Question you're all asking probably, why am I here? Or why would we ever do this? Right? So we have this question, why would we do this? Why would we imagine a number that's negative? Right? Again, a lot of people see math as utilitarian. They don't sort of see it as something you do just to do. We do this to solve problems, to model the world so that we can describe it, so we can do physics and shoot things to the moon. And now somebody's trying to raise some money to send people to Mars, which would be pretty cool, but I'm not rich enough to go, and I think my wife would get annoyed if I signed up. So probably not signing up for that one, but that'd be pretty neat. Go live on Mars, but we need math to get there. So why would we imagine -1? Well, let's go to the beginning. Before we get too carried away, let's start at the start, right? So back to the beginning. There's this wonderful thing, die ganzen Zahlen hat der liebe Gott gemacht, Alexandra ist Menschenwerk. Leopold Kronecker. So everyone knows what that means because you all know German, right? Does anyone know German? What does this mean? Can we translate it or not?
God created all of the natural numbers. Man created the rest of them.
Exactly. So the natural numbers, all of the numbers, constant numbers, so God created everything else, which man's work. So Leopold Kronecker, a great prominent mathematician a while back, not around anymore, probably a German guy, he said this. He said that God created the natural numbers. Everything else from there on was us. It was the imagination and creation in the mind of man. So let's start with what God created, according to him. 1, 2, 3, 4, 5, 6, 7, 8. That's what I mean by the natural numbers. The counting numbers. What do we teach kids? My daughter does know how to count, even though she'll refuse to do it because it's cuter, and she gets more attention when she doesn't count right. When she was like 1 1/2, she was like, count to 11, and now she's 3, she can't get past 5. So she gets more attention. Anyway, 1, 2, 3, 4, 5, 6, 7, 8. And we go on. So So these are what we call the counting numbers or the natural numbers, because those are sort of the ones we teach all of our kids, right? What do they represent? They represent a mouse. First guy, way back when, needs math. What do we need to do? I need to count how many sheep I got, right? I'm out, take care of my sheep. I've got 5 of them. Send them out to the pasture, bring them back in. Need to make sure I didn't lose a sheep, right? Or if they made a new one, I want to be aware of it. Probably won't be worth it, so I do know that. But anyway, so we got to count. So how many do I have? 1, 2, 3, 4, 5. So numbers represent quantity. We start there. Now, before I go too far, I'm going to add in the number 0. Again, this was actually a leap in our understanding of math. It seems strange to think about, but initially men and women, people, to be more gender, talk about that. They had to come up with the notion of 0, and then they added in 0. It makes sense, because right, if I've got nothing, there was that one guy, no sheep, they all got eaten by the wolf. I got nothing, so you got 0, right? Represent I don't have any. So it is sort of a quantity, even though it's nothing. But it's something. Nothing is something, something. I don't know, there's got to be something right there, but I'm not on my game. So let's imagine, we'll throw in 0 and consider the whole numbers. So that's actually what we have. We take natural numbers and throw in 0 and we call them whole. Does it because 0 looks like a whole? Probably not, because I got what we want. So it's good. We got numbers, we're doing math, everything's awesome, and then we run into a problem. So the first problem that arises is I can write equations. 5 plus x equals 3. X plus 7 equals 4, right? All I'm using is addition and equality, or basic pieces, and my basic natural numbers. And I can ask this question. 5 plus x equals 3. What does that mean? That means what do I add to 5 to get 3? What do I add to 7 to get 4? And what do I add to 2 to get 0? These expressions make perfect sense in our world that consists of just natural numbers and addition. Right? It makes sense. I can write it. But notice if all I have are natural numbers, is there a solution? No. No number plus 5 is equal to 3 if all I have are whole numbers. No number plus 7 is equal to 4, and no number plus 2 gets me back to 0. And so we can write algebra, we can talk about it, except we can't solve it. And we don't like that as mathematicians because we don't like being able to not do something. I don't think you need to be a mathematician to not like being able to not do something, right? The best way to make a kid do something is tell them not to do it, and then they want to do it, right? So, reverse psychology, but I have a feeling my daughter will use it on me better than I use it on her because she's clever and I'm cleverer. Is that clever? More clever? That's not right. Anyway, so we've got equations we can't solve. So what do? We imagine, we realize there's a number -1, right? If you think about it, can I hold -1 in my hand? Is -1 a quantity? Is -1, that's what happens when I put it in my left hand, I guess. Is -1 something I can hold in my hand? No. So in a sense, it is a product of our imagination. And we have now stepped past what God gave us and started creating, imagining, and doing this wonderful thing called being a person, right? We create, we imagine. And so we introduce this number -1. Once we define how it works, we get things like -2, -3, -4, -5, right? Just add -1 to itself a bunch of times, and we end up with negatives. We call it the integers. This is a really good word, integer. So that's what we need. We've got all of our positive numbers, our whole natural numbers. We've got 0, our hero, and we've got these new things called negative. Good stuff. We fixed math. Oh shoot, we got multiplication, right? That's the next thing we had to do. Bummer. Again, whole numbers, multiplication, right? 2 times x plus 3 equals 6, 5x equals 4, 7 times x equals 1. Again, I can write nice algebra problems, and I can't do it. What number times 7 is equal to 1? What whole number? What integer? Can't do it. We got another problem. Math is broken yet again. You might think it's still broken in some ways, probably, but we just haven't figured out how to fix it. Anyway, so we got some problems again. So what do? Same thing we did before. We invent new numbers. Now, the rational numbers are easier to work with in the sense that we can think of them as fractions. Half of a whole, a quarter of a whole, a third of a whole, 3/4 of a whole. And so again, we can think of these as quantities. We can hold them as parts of a whole. So it doesn't really strike us as something we created or invented or imagined. Quite like negatives. Negatives, you might say, represent things like debt. In physics, we think of negative as sort of direction. So we can come up with ways to interpret them. But essentially, we invented them. The same way we sort of invented fractions, and we use this idea to work. We fixed math? Not quite. Another problem. It really is a never-ending set of problems, right? So we try to fix it. Okay, addition, multiplication, exponentiation. We had a slide right at the beginning. Those were our three things, right? Addition broke it, we fixed it. Multiplication broke it, we fixed it. Let's try exponentiation. Is that going to break it? Well, of course. There's a trend here, right? Math is all about patterns, so we're going to follow the pattern. And all of a sudden, I've got something like x squared minus 2 equals 0. And there's no rational number. There's no fraction that makes that true. I could prove it to you, or you could take Math at 100 and we'll prove it to you there. Or some other class, I don't know. Maybe in the number theory seminar, we went through why square root of 2 is irrational. No, not there.
Real analysis.
Real analysis, we do it in real? Probably, yeah, that was good. Classic contradiction argument. I mean, this is a classic thing that mathematicians found out. There's a fun little story about the fact that this would be like the square root of 2. If you think of with that, we'll talk more about square roots in a minute. I'm distracted, so let's follow my train of thought. But square root of 2, again, back in the day, Pythagoras, you've heard of this guy? Remember what he did? Something about squares and some a squared plus b squared equals c squared. Yeah, he also had this like cult thing going on following him. According to some like legend, such rudeness, but it makes it more exciting. We jazz it up a little, right? We gotta make people like math, so talk about this death cult. But there was a group of people that really fundamentally did not believe in irrational numbers. Every number had to be a fraction. And when they proved square root of 2 is not a fraction, it caused some serious problems. It was like, don't tell anyone or we'll kill you. It was like a Da Vinci Code thing. Right? It was actually a big deal because it messed up their understanding of the world. The universe was broken if we had irrational numbers. Everything had to be a fraction, and it significantly bothered them. So x squared minus 2, exponents, whole numbers, subtraction, which is really just adding negatives. And my fractions are broken. And so what do? We finally accept, all right, we got to have these things like square root of 2, because I can measure that, right? I can make a rectangle, you probably call it a square, but it really is a rectangle, 1 by 1 square. Use Pythagorean theorem, and you end up with the hypotenuse being the square root of 2. So the length of a diagonal of a 1 by 1 square is square root of 2, so this is something I can measure, so therefore it should be a number if we believe numbers are measurable quantity. Okay? So we have to accept that they're out there and they're real. And so what we typically do is we teach you about the real number system, and we say we've got natural numbers, whole numbers, integers, rational numbers, and then we got these weird guys over here called irrational. That's all the numbers, we're good. I put 2 problems. Notice the same problem. I got a squared, I got whole numbers, no solution. Squared, whole numbers, no solution. Why did we only fix this one? Honestly, I don't know. Why do we stop there? Because it's the same problem, isn't it? X squared plus 1. What would I need for x squared plus 1 to be true? I need a number that when I square it, I get -1. Right? -1 plus 1 is 0. And so if I can imagine irrational numbers, why is it a leap to think of I being equal to the square root of -1 being a good, perfectly happy number? We've sort of invented and imagined negatives. Fractions we feel comfortable with. Square root of 2 we feel comfortable with because we can measure them. But essentially, from an algebraic sort of mathematical system perspective, we're doing the exact same thing. So it's really not all that imaginative at all. So let's slap that up there. The nice thing is, as soon as we get this one, we fixed it. Any equation I can write with multiplication, addition, and exponentiation in whole numbers, I can now solve. And furthermore, whatever the highest power that shows up is, that's how many solutions I have, exactly. And that's a very useful and pretty cool thing. It's called the fundamental theorem of something or other, right? It's actually a big part of that. So a complex number we can find is something that looks like this. It's a plus bi. So there's some imaginary part and there's some real part. Because what do I do if I want to add 2 and I? I'm not quite sure, so I just call it 2 plus I. And that's what we do, okay? Might seem like cheating, but it works. All right, so we've got this imaginary part, real part, where I squared is -1. And so now we get a bigger thing. Here's my little real numbers, and now we've extended to the complex. And we've fixed algebra in some sense. So, all right? Now, again, I cannot be measured. This is one of the fundamental theorem's postulates of quantum mechanics, right? Any measurable quantity has to take on a real value. I say this like everybody in here is taking quantum mechanics. How many have? A couple? Okay, good. But this is one of the postulates. Everything has to be real. Yet, interestingly enough, here's a little tidbit of Wikipedia. You can't really see it, but applications of I. Control theory, integrals, fluid dynamics, dynamic equations, electromagnetism and electrical engineering, signal analysis, quantum mechanics, something I can't read, something else I can't read, a whole bunch of stuff, all right? Without I, we can't describe the physical universe. Just like pi was essential to Heisenberg's inequality, Coulomb's law, whatever the last one was, or the cosmological thing, right? We can't do electricity. We can't be electrical engineers without I. So oddly enough, electrical engineers, if you are majoring that, expect to see a complex number somewhere in your life because you're going to have to learn about it. You need it to understand phase shifts and things like that. Quantum mechanics. So from quantum mechanics, the time-dependent Schrödinger equation, one of these fundamental things describing the quantum state of particles and things like that. What do we see in it? Even though whenever you measure things, you always end up with real numbers, we can't actually describe the universe without this imaginary component. Now, that sounds crazy, right? And then I stop and I think about my faith. I believe in a God that I can't see, I can't touch, I can't measure, right? I believe He impacts the world and created the world and guides the world. Without Him, there is no world, and yet I can't measure and see Him. So why is it a leap to believe that there's some constant, some number out there that I can't ever realize and physically hold in my hand, but it's fundamental to the underlying working of the universe? So I don't think it's really that big of a step for someone who actually believes in another aspect of this reality. Okay? And so it's sort of a nice analogy. We get to talk about, wait, did I just talk about faith in math now? Right? We don't think about these things coming together, but this is what the math department, we choose to label this because it's cool math and everyone likes it math. But there's also a lot of mystery to the world that we get excited about as Christians because we feel that understanding this helps to enlighten us and teach us something about the world we live in and therefore the creator of that world. Alright, so this is pretty cool stuff. Or at least it is to me. But anyway, a little bit more about I, because we want to finish up this equation, right? So we need to understand how it works a little bit. So we got the powers of I. That sounds pretty cool, right? What I really mean is if we take I to a higher power. So I squared is -1, that's what we defined, right? So we're good. What happens if I take I cubed? Well, I squared is -1, so if I multiply that by I get negative I, okay? And now I multiply that by I, and then I get negative I squared. But I squared is -1, so negative times negative is positive, and I get back to 1. So if I multiply by I again, I get I, and then I get -1, and then negative I, and then 1, and then I, and then -1, and then negative I, and 1, and then I keep going, and I keep going, and I keep going. So interestingly enough, what's happening with I is when I raise it to a power, it's going through this cycle. It's going 1, negative 1, negative I, 1, negative 1. It's just going around this little cycle. It's sort of strange. How many numbers, when we square it and cube it and higher power, just going around in a circle, it's sort of get that? Well, 0, right? 0 squared, 0 cubed, 0 to the fourth, everything's 0, so it's just sort of stuck there, but still, it's a pattern. 1 squared, 1 cubed, 1 to the fourth is just 1. Negative 1, negative 1, 1, negative 1, 1, negative 1, 1, going in a circle. 0, 1, negative 1, these are sort of fundamental ideas. Once again, this is a fundamental number with some very interesting patterns. Now, how do I add them? I just add the real parts, A and B, add the imaginary parts, B and D, multiplication, bunch of messy stuff, you don't really care. The point is, I can do it. All I do is multiply it out, use FOIL, and anytime I get an I squared, I replace it with a negative sign. So no matter how many powers of I show up, I can always simplify it down to just 1. So that's sort of cool, but again, nobody likes looking at this, except math people. So let's look at a picture, right? We like pictures better. So instead of getting hung up on the algebra, but I don't like standing that close, it makes me feel weird. So we'll stand back here. Let's think of it sort of geometrically. If I have a number a plus bi, the I is the imaginary part, a is the real part. What do I really have? I really have a pair of numbers a and b. And whenever we write a comma b in parentheses, we talk about this in math, where do we see this? We see this in high school geometry, right? This is a point in space, x, y. So why not draw it that way? So let's take our space, consider the x-axis the real dimension, the y-axis the imaginary dimension, and then the number a plus bi we just slap as a comma b, right? It's the point go a over here and b up. So we just pretend we're in the plane. And so complex numbers are just geometry. Okay, it's just like regular old planar geometry. That's pretty cool. Now, what would it mean to add 2 points? In geometry, do we talk about adding points? No, we introduce something called vectors, and we add vectors in linear algebra. Do we multiply points? Not really. And once we get to linear algebra, do we multiply vectors? Not really. We have a dot product and a scalar product, or not scalar product, that's not two both vectors multiply, that's a scalar product. And we have this thing called a cross product. And so we have ways of multiplying them, but it doesn't say, here's a vector multiplied by another vector and I get another vector. Okay, so geometrically, we've never really had a way to talk about adding and multiplying points. But we think of them as complex numbers. Adding points is just adding vectors. So if I think of the point here, 3 plus 4i, it would be this arrow to that point. 1 minus 1i would be that way. And if I want to add them, I'm just going to draw them head to tail and connect the job, make a triangle. So the sum of the red and the green arrow is the blue arrow. And when I add them up, that's actually what turns out in the arithmetic. So the arithmetic matches up to just vector addition. So this is pretty cool because anyone who learns linear algebra already knows how to multiply complex numbers. Right? The neat feature is now all of a sudden I can multiply points. The way we multiply ends up corresponding to adding the angles and multiplying their magnitude. So if I have a complex number at angle like here, and I have another one at this angle, what do? I take those two angles and add them together. And then I take their lengths and I multiply the lengths. So if one was length 2 and one was length 3, you multiply that and you get 6. So I'm going to draw an arrow 6 distance this way, add it up there. And so multiplying has to do with rotation and scaling. And we've now defined a way to multiply two-dimensional points or vectors. Okay, so you can think of complex numbers as really just geometry with some extra stuff to it. Okay, it will give us some more things to do. So that's sort of neat. This imaginary number is just geometry. So all the math sort of comes back around. Sort of neat. All right, let's take a little video, because everyone likes to watch videos, but I'm running short on time, so we're going to skip the video, because I don't want to take 5 minutes. I'll show you a picture of it, and then we'll get back on track. Oops. That's not where I was going. All right, let's go back to the video. So I'm just going to zoom through here a little bit. This is what's called a fractal. This is just like, I'll talk. So they made a video of Mandelbrot set. This picture, all of the wonderful, beautiful pictures we see here is self-similar. As we dive in closer and closer, we keep seeing the same structures repeat themselves over and over. All we're doing is zooming in really, really close. All of this comes from just taking complex numbers and multiplying them by themselves and adding. So take a number, square it, add 2. Square it, add 2. Square it, add 2. Square it, add 2. Do that over and over again, take the limit. And we can visualize the results as this wonderful, mesmerizing, hypnotic picture. So it's sort of a neat thing that we can actually get these beautiful imagery just by applying the notion of a limit repeatedly to complex numbers. So we get some really cool stuff, and we can sit here for hours and probably not get bored. We just fall asleep or so. My fun little joke. I jumped in now. Anyway, who is that? That's a bike. That's my dog, who is in Dunn Hall right now. Mine's here, but she's over there playing. So let's get back on task. Exponentiation revisited. So the last thing we have to do, we have all the pieces, right? We've got addition, we've got equality, we got 1 and 0, now we know what e and I pi. So the last thing to do is put it all together. What in the world does e to the I pi mean? Right? I know the pieces, but what does it mean to come together? So again, let's start at the beginning. Exponentiation, natural number. Notice what did we do? Natural, whole, integer, rational, irrational, complex. We went through this, so let's go through it again. Patterns. We like patterns in math, right? What does it mean? 2 to the 5th means, right, 2 times 2 times 2 times 2 times 2, 5 times. Makes perfect sense. What if I want integers? What if I have like 2 to the 0 or 2 to the negative 5? What would that mean? Well, what do? We follow a pattern. So look at this pattern. 2 to the 4, 16. 2 cubed, 8. 2 squared, 4. 2 to the 1, 2. So if you think about it, as I go down, 4, 3, 2, 1, what's the pattern? Divide by 2, divide by 2, divide by 2. So let's keep the pattern going. Divide by 2, 1. So 2 to the 0 is 1. Turns out x to the 0, we're going to call that 1. Keep going, divide by 2 again. 2 to the negative 1 is a half. Go down again, 2 to the negative 2 is 1 over a half squared. 2 to the negative 3 is 1 over a half cubed. Each time I'm going to multiply by 1 half, divide by 2, and we see that x to the negative is just 1 over x to the positive. So we can define it for negatives just by following patterns, Billy patterns. What about a fraction? So let's... Quarter to 1 half, we have a fraction. We have to make meaning of this. We're really inventing, we're creating the whole time. We're inventing. People say, math people, let's, right brain, left brain, we think analytically, we're not creative. We have no imagination. I think we have a lot of imagination in math, and we're quite creative. You just have to look at it the right way. All right? So we look at it this way, and we have 4 halves. So what would happen if I square it? Well, I know, it's been a while for some of us. Power to a power, what do? Multiply, right? So 1 half times 2 is 1, so 4 to the 1 is just 4. So if I take 4 to the 1 half and square it, I get 4, and so that means is 4 to the 1 half has to be the number which is squared to be 4. We call that square root of 4 or 2, right? So fractional exponents, we can think of the denominator q as just a root, the qth root, the square root, the third root, the fourth root, and then the p is just a regular old exponent. So we can either do x to the p and then root it, or we can do the root and then the p, pick your order. We give you options in math, right? 2 options. You're supposed to give your daughter 2 options so she feels like she's in control, but you can control what she does. My daughter's smart enough to be like, I don't like those 2 options, give me another. You read parenting books, you try it, it doesn't work. You give up. That's not how you get it. Anyway, some of us don't. So we got fractions, we're good. So what do we do with the irrational, right? That's the next problem, I think. Well, we don't really know how to handle them, but from real analysis, we learn that we can actually, for any irrational number, I can come up with a sequence of rational ones to converge to. Go back to that very beginning when we had those circles with the polygons. The goal was to use a rational number, the polygons, to approximate this irrational number, and as I did it over and over and over and over again, I got closer and closer and closer and closer. And so again, what they were doing when they were trying to approximate it is they were doing calculus and they didn't know it. Okay, we just need to call it that guy. And so calculus says we can always find a limit of rationals which go there. So what we do for an irrational is we just take the limit of the rationals and say, let's just look at those and use that. Okay? So we avoid the problem, because why fix it? Right? We fix it by avoiding it. That usually doesn't really work in the real world, but math isn't the real world always, and it's a lot better. So now we have this y equals a to the x thing. It works everywhere, everything's good, we're happy. We want to do complex. I got an I here. I need to handle it. The pi is irrational, so I need the pi irrational. But now I've got complex. We're going to do complex. I'm sorry, here's a really bad mathy slide. I couldn't get away from it. I know, I was trying very hard not to go at me. But in order to handle complex ones, in Calculus 2, we talk about something called Taylor series. Yes, this is a Maclaurin series. Don't try to be smart at it. I do know. But it's a Taylor series. E to the x, this function, now that we've done it for irrationals, we can actually add up an infinite number of other numbers, which are just good old-fashioned numbers, and do exponentiation happen. Sort of a magic fun thing. So if we want to do irrationals, what do? We just use this expansion and do irrationals. We cheat. Nice thing is, I can square complex numbers, I can divide complex numbers, I can add complex numbers, right? We have all this geometry. So this makes sense to do, and it matches what we did before, it fits the pattern. So let's define it that way and say, let it be. I'm not saying I'm God, but let it be. Right? We're defining it this way. Creating our complex exponential. But again, what in the world is this? So when we do Taylor series, we don't just talk about exponentials, we also think about everybody's favorite function, sine, cosine, trigonometry. We all love trig, right? A couple people in the room do like trig. We get these fun things. If we remember what happened with I when I raised it to powers, I squared, I cubed, I to the fourth, what does it do? It goes 1, I, -1, negative I, +1, positive I, -1. It follows that pattern, right? And notice what happens. I've got my 1 minus theta squared plus theta to the 4th. 1 minus theta squared plus theta to the 4th. It fits the pattern. I've got my I theta, negative I theta cubed plus I theta to the 5th. So if I just take this I and throw it out, right, pull it out, I've got theta minus theta cubed plus theta to the 5th. And so what I really have here is cosine plus sine with an I attached. All I'm doing is factoring. I know it's scary, but factoring is all of them. And a little calculus, but let's pretend it's not there. And what we end up with is Euler's formula, e to the I theta equals cosine theta plus I sine theta. Now, what in the world does that mean? Now we have trigonometry, I just made it worse. Sometimes we have to make things worse to make them better. Go back to trig. If I have a point cosine sine, that's really a point on the unit circle. Right? If you remember trig, that's what it is. All right, cosine is adjacent, sine is opposite, so we get my x and my y coordinate. And so cosine plus I sine, so sine is my imaginary, so that's my y. Cosine is my real, so that's that. And I end up right here on the unit circle. So e to the I theta is the point on the unit circle with the angle theta. That's all it's saying. So all this crazy calculus boils down to a simple geometric idea that e to the I theta, e to the I something is just some point on the unit circle, that angle. So what theta do I have? Pi. What angle is pi? 180. So what is e to the I pi? It's just the point on the unit circle, which is 180 degrees, so right here. And what is that? That's the point negative 1, 0. Negative 1 is my real part, 0 is my imaginary, so number 1 plus 0i is just negative 1. E to the I pi. Combine 3 of the most important constants in mathematics, and you end up with the opposite of one of the others. Move it to the other side using the basic algebra, and we've got Euler's identity. E to the I pi plus 1 equals 0. So what does it mean? I don't know. But it's pretty neat because it ties in geometry, it ties in algebra, it ties in our fundamental understanding of numbers and operations and everything we do in one nice, concise form. Courtney Taylor, Dr. Taylor, wrote a little blurb that we sent to some prospective students. Some of you might have actually gotten this, depending on how old you are. And in it he says the following. In a remarkable surprising convergence, Euler's identity relates basic operations of addition, multiplication, and exponentiation with the fundamental numbers 0, 1, pi, e. Euler, a committed Christian, installed the study of mathematics as an act of worship. In the Anderson University Math Department, we agree. Truth is found in Jesus Christ. Studying his created world, seeing all these amazing, crazy, different ideas, all these different shoots of math that seem unrelated, tie back together in one place. I think that's amazing. I think that's beautiful. God's order is infinite complex. It's amazing what he created, how it weaves together, how it works together, how our cells interact in chemistry, and all of this stuff ties together to make us what we are. And we see it once again in mathematics, and that is just flat out amazing. Aristotle, mathematical sciences particularly exhibit order, symmetry, and limitation, and these are the greatest forms of beauty.
I noticed that the transcendental numbers, at least the ones we looked at tonight, e and pi, square root of -1, are all small numbers. Are there other transcendental numbers that are larger or bigger or shorter? Why are they all just small numbers centered around 2, 3, 1?
That's a good question. There are plenty of large transcendental numbers and irrational numbers. Again, I made the comment that, for instance, irrational numbers are actually more plentiful than rational numbers. It seems a little strange, but if you study some set theory, for instance, in Math 1250, our new class called Explorations in Math for the Liberal Arts, I actually go through and justify that. But you can actually argue that there are infinitely many more of these strange numbers, irrational, so they can get as large as you want. Why the fundamental important ones are so small, I don't don't know, that's sort of a neat mystery, so I don't have a good answer there. But again, it's just one more thing that highlights the amazing fact that this very simple, small body of knowledge gives such a complex structure to our world. It's just amazing to study and see how these things come.
Euler's identity. Euler was a Christian. What kind of mathematician was he? Is he good at identity?
Yeah, no, Euler was a pretty good one. He did quite a bit of stuff. In fact, like I said, Euler's number is named after him. This identity came in the early 1700s. It was known. He worked on a wide range of problems, spanned all of mathematics, and so a lot of things are attributed to him that he didn't necessarily invent, but he used them in creative ways. So Euler's one of the great mathematicians out there and did a lot. I mean, just a wide variety of stuff. And I think if you study a lot of the scientists and mathematicians back in the 1700s, 1600s, their faith actually was something that motivated them to study structure, right? A lot of the early physicists, like Ampere, I believe, that amps are named after. I remember from way back when I was a student learning about him, he was a committed Christian. I think Maxwell, I heard a story about, he described all electromagnetism in 4 equations. Maxwell's equations were a big deal. And he had 3 that he had experimental evidence for. And he said, this 4th one has to be true because I believe in a beautiful symmetric world because I have a creator that created the world. So he threw out a 4th equation that he had no evidence for, purely based on his faith, his belief in this structure. And then years later, it was actually solidified, and they came up with experiments that showed that it was true. And so a lot of the original people who were doing this, they were seeking to understand creation out of faith base. And it's only in sort of modern times that we've lost that and started to separate the two and say that science is something that's sort of opposite of it. It's completely like 180, which is the pie. It's not the pie. It's one more.
Any other questions? Let's thank Dr. Lambright.